Many times in the real world, scientists are interested in being able to recreate the results of an experiment and investigating how to undo the steps they have followed. This process involves the application of inverse functions, and that's what we will be examining today. Hi, my name is Jason Rosenberry, and in this lesson we will also explore logarithmic functions. Let's start with a definition. One-to-one function. A function f is one-to-one on a domain D if f of a does not equal f of b whenever a does not equal b. Let's look at some graphs that will help illustrate this definition. These graphs show how we can use a horizontal line or the horizontal line test to determine if a function is one-to-one. Since each output of a one-to-one function comes from just one input, a one-to-one function can be reversed and send outputs back to the inputs from which they came. And the function defined by reversing a one-to-one function, f, is the inverse of f. So again, with these two graphs, notice that the first graph we have y equals the absolute value of x. We can find a horizontal line that intersects the graph in more than one place. Notice we have found a horizontal line that intersects this graph more than one place. This one is not one-to-one. Versus the second graph of y equals the square root of x, we cannot find a horizontal line that intersects the graph in more than one place, so this one is a one-to-one function. The symbol for the inverse of f is f to the negative 1. The symbol for the inverse of f is f inverse. The negative 1 in f inverse is not an exponent, so f inverse of x is not equal to 1 over f of x. The result of composing a function with its inverse in either order is the identity function. In other words, if f of g of x is the same thing as g of f of x, which both give you just x, then f and g, those two functions, are inverses of one another. Let's now look at how we can find an inverse for a one-to-one function. Writing f inverse as a function of x. Solve the equation y equals f of x for x in terms of y. Interchange x and y, and the resulting formula will be y equals f inverse of x. Now it's time to try some examples. Find f inverse of x and verify that f of f inverse of x equals f inverse of f of x equals x, for f of x equals x cubed minus 1. So let's start by substituting y in for f of x, and our first step is to solve this equation for x. So we would get x cubed is equal to y plus 1. Now taking the cube root of both sides, we get x equals the cube root of y plus 1. Now that our equation is solved for x, we go ahead and interchange all x's and y's. So this would give y is equal to the cube root of x plus 1, and this is f inverse. So we can now say f inverse of x is equal to the cube root of x plus 1. Let's now verify that these two functions, f and f inverse, are in fact inverses of one another. To do so, we need to show that f of f inverse of x is the same thing as f inverse of f of x, and that they're both equal to x. Let's start with evaluating f of f inverse of x, which is equal to f of f inverse of x. So making this substitution, we would have f of f inverse function, which is the cube root of x plus 1, and substituting that into function f, we would get the cube root of x plus 1, that all cubed, minus 1. And as you can see, the cube and the cube root cancel each other out, leaving us with x plus 1 minus 1, which is equal to x. Let's now test f inverse of f of x, which by definition is f inverse of f of x. So making our first substitution, we would have f inverse of f of x, which is x cubed minus 1. Substituting x cubed minus 1 into f inverse gives us the cube root of x, which is the quantity x cubed minus 1 plus 1. This would then simplify to the cube root of x cubed minus 1 plus 1 is just x cubed, and the cube root of x cubed is x. Therefore it verifies. Find f inverse of x and verify that f of f inverse of x equals f inverse of f of x equals x, for f of x equals 2x plus 1 over x plus 3. So again, we will substitute y in for f of x equals our fraction on the right hand side. We want to go ahead and solve this equation for x. So we'll start by cross multiplying. So 2x plus 1 would equal x times y plus 3y. Again, we want to solve this equation for x. So we would have, subtracting xy from both sides, 2x minus xy equals, subtracting 1 from both sides, 3y minus 1. Factoring out an x from the left, we get x times the quantity 2 minus y is equal to 3y minus 1. Dividing both sides by the quantity 2 minus y gives us x equals 3y minus 1 over 2 minus y. We now interchange all x's and y's, so we get y is equal to 3x minus 1 over 2 minus x, and there is f inverse. So f inverse of x is equal to 3x minus 1 over 2 minus x. And it does verify that f of f inverse of x is equal to f inverse of f of x, both giving you x. Let's now turn our attention to logarithmic functions. Base A logarithmic function. The base A logarithmic function y equals log base A of x is the inverse of the base A exponential function y equals a to the x power, where a is positive and a cannot equal 1. The domain of y equals log base A of x is from 0 to infinity, not including 0, as is the range of y equals a to the x. The range of y equals log base A of x is all real numbers, as is the domain of y equals a to the x. Since composition of inverse functions in either order leads to the identity function, we have the following inverse properties for a to the x and log base a to the x. Inverse properties for y equals log base ax and y equals a to the x power. Property 1, we have the base a property. A to the log base a of x is equal to x. Also, log base a of a to the x is equal to x. For a values greater than 1, x needs to be positive. Also for base e, e to the log base e of x is x. Also, log base e of e to the x is x for all x greater than 0. Let's try an example. Solve for y. natural log y equals 2t plus 4. We'll use the inverse property of natural log raising e to each side of the equation to get that y equals e to the 2t plus 4, meaning we can base e both sides of this equation. So base e the left, we get e to the natural log y equals e to the 2t plus 4. And then using property from the previous page, e to the natural log y is just y. And that leaves us with y equals e to the 2t plus 4. There are three other properties of logarithms we need to review. Properties of logarithms. For any real numbers, x greater than 0 and y greater than 0, we have what's known as the product rule. Log base a of x times y is equal to log base a of x plus log base a of y. We have the quotient rule that says log base a of x over y is equal to log base a of x minus log base a of y. Power rule. Log base a of x to the y power is equal to y times log base a of x. Solve the equation algebraically. We have 1.045 to the t power equals 2. Let's start by taking the natural log of both sides of this equation. So we will have natural log of 1.045 to the t power equals the natural log of 2. On the left-hand side, we can use our power property of logs. So natural log of 1.045 to the t power is the same thing as t times the natural log of 1.045. On the right-hand side, we have natural log 2. And now to solve for t, we can divide both sides by natural log of 1.045. So t is equal to the natural log of 2 over the natural log of 1.045. And that's an exact answer. We could use our calculator to approximate if needed. Finally, we want to look at a formula that will allow us to change the base of a logarithm to another base. The change of base formula. Log base a of x is equal to the natural log of x over the natural log of a. This formula can be used to change to any base, but we've written this formula in a convenient fashion since the natural log is a base that's on everyone's calculator. Let's use this. Draw the graph and determine the domain and range of the function y equals log base 2 of x plus 1. Now our problem is with most calculators, they can only handle base 10 or base e. So we cannot just simply ask the calculator to graph y equals log base 2 because of it being in base 2. So using our change of base formula, we start with y equals log base 2 of x plus 1, and using change of base formula we can rewrite this as y equals the natural log of x plus 1 all over the natural log of 2. And as you can see on the left hand side, our calculator can graph this function, which we have here on the left hand side. Let's go ahead and find the domain and range. Looking at the graph, we see that the graph goes, in terms of the domain, from -1 to positive infinity. X cannot equal -1 because we cannot take the log of 0. So it's from -1, not including -1, to positive infinity. And the range is all real numbers. Now it is time for you to try a problem. Draw the graph and determine the domain and range of the function y equals log base 2 of x. Pause the video while you work on this problem. When you are finished, restart the video to check your solution. So starting with y equals log base 2 of x, we'll first use the change of base formula, giving us y equals the natural log of x over the natural log of 2. Using that, plugging into the calculator yields the graph here on the left-hand side. We can see that the domain of this function is from 0, not including 0, to positive infinity, and the range is all real numbers. In this lesson, we explored inverse functions, including the logarithm and exponential functions and their graphs. Be sure to work the exercises that your teacher assigns, and we'll see you next time.